to understand resistors or circuits, we need to have the idea of equivalent resistance. We really have to have that down pat. And so basically, equivalent resistance is, you'll see it abbreviated two ways: REQ, the resistance equivalent, or RT, meaning like the total resistance. Basically, these different resistor setups, these different circuits, behave as if they were a single resistor. And that's what we want to do, is we want to boil this big one down here, this big one that is our series circuit, or this big parallel circuit. We want to boil them down into one resistor. So there's only one resistor. Because remember, in the last one, we went V equals IR. And if we knew the voltage and we knew the resistance, we could find the current. Or if we knew one of the others, we could find the voltage on the battery. So there will always be two that you know and one you're looking for. And so that's what we're trying to do here. We're trying to figure out how does this behave? How does this circuit behave as if it were a single resistor? How does this whole circuit behave if it were a single resistor? So in a series circuit, your equivalent resistance is basically the sum of all the resistors. So you're going to take the first resistor and you add it to the second resistor, third resistor. If you had a fourth resistor, a fifth resistor, however many resistors you're going to have, you're going to add them all together. And so really, a series circuit has a huge amount of resistance. And so a lot of resistance, it's generally going to have a small current. So these are generally going to have small currents. And the reason is this: after the current goes out of the battery, it comes out of the battery, and then it sees this resistor, and it's like, okay, I got to go through that. And then it sees this resistor, and it goes, okay, I got to go through that. And then it sees this resistor, okay, I have to go through that one too. And this is kind of like if you're at the grocery store, and you have to get through the single checker, and then you have to go through the single door to get out. And then once you get out, there's somebody checking your receipt to make sure you have everything you bought. And all of that is going to slow you down as you get through the circuit. So this resistance, it's also like the really long wires. Because remember, the resistance is equal to the resistivity times the length divided by the cross-section area. So if you have a long wire, this is kind of like a long wire. I have to go through this, I have to talk to all those guys, I have to talk to all those guys, and then I have to talk to all those guys before I get back to the battery. So two different ways to think about it. Either way, you're going to end up with a big equivalent resistance for a series circuit. Okay, and then in a parallel circuits actually, in the whole, they have less resistance, because this is like being at the grocery store. If we only had one checker open, so let's say that all of these were closed, okay, you could only get through that line. But once we open another line, now we can get through faster. Oh, we're going to open another line, we can get through even faster. So you starting to see how the current can speed up. We can get more electrons total through. And so that's kind of what we're talking about, is how much total current can get through this circuit. So the equivalent resistance for a parallel circuit is much smaller than that for a series circuit. And so a lot of our things actually run on parallel circuits. And the way we do it is 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over, you keep going till you run out of resistors. So this one would go up to R4 because we have 4 different resistors. Now, one of the things you want to get used to is on your calculator, there's a button that says x to the minus 1. That x to the minus 1 button is 1 over. So let's just do one quick practice, because series is really easy. You're just going to add them up. That's not a big deal. But let's do one quick practice problem with parallel, just to kind of show how it would work. Okay, so let's say we had this parallel circuit where we had a 3 ohm, a 4 ohm, a 5 ohm, and a 6 ohm resistor on it. We would go 1 over Req is equal to 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6. Now you see how you have all these fractions and you could do the whole common denominator thing, but are you starting to see that this would be kind of ugly? So what we're going to do is in our calculator we have 1 over Req, and we're going to 3 to the minus 1 plus 4 to the minus 1 plus 5 to the minus 1 plus 6 to the minus 1. And that'll give us, altogether this came out to 0.95. Now one of the things we need to understand is that this answer here, the 0.95, is 1 over Req. Okay, we haven't done this, we haven't taken apart that yet, so we have all that stuff. So then we need to flip that over, and that'll give us 1 point something. That'll give us 1.05. So we get Req is 1.05 ohms. And then using this and knowing the voltage of the battery, we could find the current that leaves the battery. So the equivalent resistance will help us find the current from the battery. So I guess we should do something like that also. So next page. Okay, so here's what we know. We know that our equivalent resistance is 1.05 ohms. That's how all of these behave as if they were a single resistor. So we just took all 4 of these guys and squished them down so that they became that one resistor. And then let's just say, because it doesn't give us a battery, so let's make up a battery. So let's say this is a 12-volt battery, so it's a car battery. You don't need to know that. So it's a car battery, and so we want to know what is the current that leaves the battery. So we go V equals IR, our favorite equation. We know it's a 12-volt battery, and we don't know the current, but we do know that the equivalent resistance is 1.05. Okay, so then we can solve for that, and we get 11.4 amps. Okay, that's the current that leaves the battery. Okay, that's the current that leaves the battery. But remember that that current then splits up between the different resistors. So some of that current is going to go this way, some of it's going to go that way, some of it's going to go this way, some of it's going to go this way, some of it's going to go this way. But these currents, when we're done with those, we're just going to go V equals IR for all of these guys. But all of those currents are going to add up to the current from the battery, because that's a property of a parallel circuit, is that your voltages are the same. So all of these guys, if this is a 12-volt battery, 12 volts, 12 volts, 12 volts, 12 volts. These were all 12 volts. So this one, V equals IR, 12 equals I times 3. So this one has 4 amps going through it. Let's find a color that actually won't interfere with everything. So through this first resistor, we have 4 amps going through. Through this second resistor, because these are all 12 volts, don't forget they're all 12 volts because this is a parallel circuit, and so those voltage is the same through every single one of them. So 12 equals I times 4. So here we get 3 amps going through this one. We get 2 amps going through this one. I'm doing the ones with the easy math. And then, 12 divided by 5. Ooh, I think that would be 2.4 amps. And if we take these 4 currents, 4 and 3 is 7, 11.4, or 9.4, and 2 is 11.4, and see how they added up to the current that came from the battery. So that is a huge big check for us, that our currents all added up to what comes from the battery. These were simple ones, and in the next one we are going to do a combination circuit, which is a little bit more complicated.